Good evening. Good evening, everyone. Where are my freshmen at? We've got freshmen? Woohoo! Okay, good, great. Just wanted to see how many were here. Welcome. My name is Nirmal Trivedi. I'm the Director of Academic Transition Programs here at Georgia Tech. And on behalf of the Library and Information Center and the First Year Reading Committee, it's my pleasure to welcome our faculty, our staff, our students, and especially our first year students here to our annual First Year Reading Lecture. We are absolutely delighted, absolutely thrilled to have Professor Norman with us today. The relevance of tonight's talk really sort of hit when looking at Wired Magazine's September issue. I'm not sure if any of you have seen it, but it's the next slide, yeah. Is that better? Okay. The September issue of Wired Magazine had this sort of as their feature article, and I tried to figure, does anybody see the issue here? Is there something missing here? And it took me about 10 minutes to figure out, well, this didn't look right, but then, you said it does look right at the same time. It was an interesting sort of realization. What was really particularly interesting was the next sort of comment here in the magazine by one of the writers. He said, without proper design, without considering how new products and services fit into people's day-to-day lives, any new technology can be terrifying. That's where the challenge comes in. The task of making this new world can't be left up to engineers and technologists alone. And I thought that was quite a provocative statement, and one that was sort of directed, I think, a lot towards our students here at Tech in some ways. So is this true? Is this actually the case? And I think tonight's talk might give you some ways to respond to such a commentary. This morning, he already has spoken to a mixed group of students and faculty from interactive computing, industrial design, psychology, digital media, all over there in Technology Square. And tomorrow he'll be interviewed on our own radio station, WREK 91.1 from 12 to 1 on Lost in the Stacks, which is our homegrown version of Terry Gross's Fresh Air. And if you're over 30, you know what I'm talking about. From 2 to 3 tomorrow, he'll be our featured speaker in a panel discussion with Tech faculty on human-centered design. And that will take place in the College of Architecture auditorium. So in addition to, so there are also programs happening all over the Tech campus. And if you look at, there's a brochure in the back, and also here you'll see there's going to be a Bad Design in Atlanta contest that takes place in all of October. There are design tours of Atlanta, and in housing, if you're living in the dorms, there are these things called Hot Topics dinners, which are taking place. Their faculty come into the dorms and have conversations with the students who are there on the subject of the book and their own research. So these are nice moments in which faculty can engage one-on-one with the students, and the students can ask questions. And it's all revolving around Living with Complexity this year. The details for all of these events, of course, will be available on our website, enrichment.gautech.edu, and on our Facebook site. Which, if you like us, you'll get some updates. And I guess liking is, can mean many things. And one more, Allison. So of course, I want to thank Professor Norman for committing all his time to all these interactions. And of course, none of this would be possible without the tremendous university-wide support for Professor Norman's visit and the First Year Reading Program in general. And I wish to especially thank the Vice Provost for Undergraduate Studies, the College of Architecture, the Library, the School of Literature, Media, and Communication, and GVU, Graphics, Visuality, and Usability. All have really contributed much to making all of this happen. And we have more sponsors across the university who have also helped us make sure that this program has gone off well. And those are just the sponsors, some of the other partners on campus that have helped us. I think over time, year by year, this program is growing. More students are getting to know about it. More students are getting excited about it. I think especially in their later years, and they're talking about it, and it's like, oh, this is a great thing for freshmen to do. And I think it's a program that can develop year by year into something even greater and better. And I really welcome all of your input into making it such a great program. In fact, I really sort of request that you contact me and say, hey, this would be a great idea for a book, or this would be a great idea for a program that you could do. Or, hey, how about all freshmen actually do a project their first year together? So let's talk about these possibilities. So before I turn it over to Dr. Potts, I just want to mention a couple logistics. After Professor Norman speaks, we will open up the floor for some questions, and there are mics in the aisles, so you can go ahead and come up. As you know, the first question is always really the hardest, right? So if any of my students are here, I'll give you extra credit if you come and ask the first question. But the first question, I'll come up and ask it. After our Q&A period, Professor Norman will sign books just outside the auditorium, and there's also going to be a reception. And of course, if anybody would like this copy signed by Dr. Norman, he'll be happy to do that as well. It's now my pleasure to introduce Dr. Colin Potts, who will introduce our distinguished speaker. Dr. Potts is a vice provost for undergraduate education. His PhD is from psychology from Sheffield University, where he studied research in text memory and recognition. He joined the faculty in 1992 in what is now the School of Interactive Computing. And his research over the last 25 years has spanned the fields of software design methods, human-computer interaction, and information privacy. And he is best known for design methods that start not from technology innovation, but from user needs. Please welcome Dr. Potts.
Well, I'm the only person standing between you and our speaker today, so I'll be brief. But I wanted to make 2 points. One was about the book program and the selection of the book itself, and the second is about Don's distinguished career, and they both come together essentially. Some years we ask freshmen to read books that really take you out of yourself and see the world through others' eyes. People who are dealing with certain predicaments, for example, and make you think about the relevance of what you're studying in the light of social issues. And we had a very interesting book that we chose along those lines last year. This year we thought we'd do something different and ask ourselves, what kind of people are you and what do you have in common? And in starting your careers here at Georgia Tech as students and your careers as budding professionals, what is it that you do? And in many ways, you're all designers, or at least you're all faced with the challenges of technology. And that's obvious in the case of those of you who are majoring in engineering or computer science or architecture or design. But it's also true, I think, if you're pure scientists or business majors or in the Ivan Allen College as critics or historians of technology, or people who are interested in the dissemination and entrepreneurship around new ideas. And everything is essentially design. Arranging this visit was, to some extent, planning as a form of design. Organizing a course, a course curriculum or a degree program is a form of design. This building was designed. And so we're all involved in the process of bringing about change and making things, whether they're physical things or virtual things, and reflecting on that and the fact that just coming up with cool, neat ideas isn't enough, but that our ideas have to mesh with people's needs, the way they work, and not only in the grandiose sense of not falling down and harming people, but also just simply making life worth living and convivial and congenial and comfortable is a really, really important, I think, thing to internalize. And so we wanted to start a conversation across the campus, really from the very first, your very first introduction to your experience into the Georgia Tech way, that if you're going to change the future, it's very important to do so in a way that's humane and actually really meets everyone's sort of needs and aspirations. And that, in fact, is really, I think, one of the inspirational messages of of Don Norman's latest book, that we live in a world of complexity, and we have to manage that. We have to recognize that and not dumb it down or wish it away, but not respond to it by confusing people and teasing those two ideas apart. Complexity and complication, I think, is a really important and in retrospect, perhaps obvious idea, but one that really needs to be repeated. I met Don Norman, I think, for the first time in the pages of a book that he wrote when I was an undergraduate. And it was something that, in fact, earlier today was waved at the audience of the GVU Brown Bag. It was a book that in my course curriculum was abbreviated as HIP. It was a HIP book by Lindsay and Norman, Human Information Processing. And in the nicest possible way, it eventually drove me out of psychology. And I say in the nicest possible way, not in the sense that, oh God, I can't stand any more of this, I've got to find something else. But it was my introduction to a way of thinking about, dare I call it, the human mind, mental processes, that was infused through and through with computational thinking. And more than metaphors, but models that were based on notions that really come from engineering, paying attention to things being a form of selective attenuation of signals or filtering, for example. Working memory being a form of buffering while information is being processed or consigned to longer-term storage. And these are very powerful ideas that made me start thinking, the action's actually in computing, and that's where I wound up. But it was a very influential idea, and a few years later, I don't know, we remember the conference at Gmunden in Austria. I think it was in '82. Rather cozy little lakeside town. This was, I think, probably during the formative years where Don was still a distinguished, actually, academician and researcher in experimental psychology, but wound up shortly thereafter, well, not shortly thereafter, but writing a book for which I think is very well known, the Design of Everyday Things. It was originally the psychology of everyday things, but design sells and psychology doesn't. And it's actually sold, I think, 500,000 copies, and it's about to be republished on the 5th of November, which for those of you who are also British isn't the most auspicious of dates, because that's actually bonfire night, but we will not be consigning that book to the flames. So it's been a very influential book about how design can be made more humane. One more thing, after leaving the University of California, Don embarked on a career initially, I think, with Apple, and was partly responsible for leading the development of this wonderful device, which I found in my office today. It's the MessagePad 120, the second generation of the Apple Newton, with its tricorder flip-over screen protector and retractable stylus. I actually loaded it with 4 AA batteries earlier today, and it went pling, but that was all. It's dead. But nevertheless, it was ahead of its time, and really, I think the whole stream of PDAs from the late '90s down to modern smartphones really stemmed from this innovation. So the reason that Don Norman's here today is not just because he's the author of today's book, this year's book, and I think very influential and I hope thought-provoking book, but also because I think he's a role model for many of you in that it's possible to have a distinguished career in terms of scientific depth and rigor, and to reach out at the same time and address applied issues, to become a public intellectual, and to engage with the public about what really matters in life. And that, I think, is very, very important, that we don't think of what you do here as becoming a clone just of professors, but of engaging with the real importance of the technology that you either develop, critique, deploy, or discover the fundamental inventions, fundamental theories that they lead to. So it's my great privilege to welcome, and I hope you give a hearty welcome to Dr. Don Norman.
Thank you. I haven't seen one of these in years. There's an interesting story about why it failed. Apple was really proud of its handwriting recognition. We had gotten an advanced group of Russians who did this really advanced handwriting recognition that used advanced mathematical nearest neighbor algorithms. And actually, if you understood handwriting recognition, you were really impressed with what it did. There was only one problem, is that it didn't work. It worked most of the time, and the developers of the Newton were fantastic at using it. They could write and it would recognize everything they wrote. But the rest of us struggled and struggled and struggled. And yet, if Apple would have said, this is a great device, it's really sort of, in some sense, the iPad. And it allows you to read books. We had travel books in it. And allows you to take notes and allows you to do all sorts of things. And to take notes, well, you just touch here and there's a keyboard and you can touch on the keyboard and all that. And they wouldn't have mentioned the handwriting recognition. And a few people would have discovered it and maybe learned to use it. But no, that wasn't Apple. Apple said, it was fantastic. You could scribble the note and do this and do that. And, well, you couldn't. And the problem was this. So Trudeau, in his comic strip, showed off this Newton. And he would write on it, and he would write one thing, and out would come something completely different, and write this, and something completely different. And so Trudeau's comic strip is what killed the Newton. And the problem was this. When I write a word, it was recognizing them word by word. Not letter by letter, but word by word. And so it found the nearest mathematical match to what it thought you had written. And it was actually pretty intelligent, except that to the human, I don't know what the mathematics behind that is and what this weird multidimensional space you have. And so I write happy, and it writes Santa Claus. And what? So I blame the machine, stupid machine. A few years later, these two young kids put together another device, which they called the Palm Pilot. And they decided to have handwriting recognition. They decided to do it letter by letter. And they did is they said, we're not going to let you use your normal handwriting. We're going to teach you a way of printing. And they invented an alphabet where every single set of strokes was uniquely different, which made it fairly easy to do the recognition. But they were very clever. So it was sort of similar to the way you write anyway. So that was an A, and that was a B, and that was a C. And so they taught you this, and you could learn it pretty well, pretty quickly. And the difference here is that because it recognized letter by letter, it would often get the word but miss a letter or two. And it actually was not as good as Newton's handwriting. It made more errors. But when you made the error, you said, that's my fault. Oh, stupid me, I made that H and it looked like an N because I didn't make that line big enough, right? So you could see why you made the error and you blamed yourself. Now, the weird thing is, blaming yourself is a good thing here because it made you accept it and say, I'm going to learn to write better. Whereas in the Newton, instead of what we try to tell people, learn to write more neatly, no, you blame the machine. Now, that's actually just the opposite of the message I always preach, which is, if you have problems using technology, it's not your fault. It's the machine's fault. Newton is sort of the opposite of that. Too bad, though. It was a really neat device that did many things that we still don't do quite today. That's an aside, triggered by the fact that you brought it. You know, on the way here, I had an interesting experience. I was waiting in line at the San Jose airport to board my Delta flight, and I'm way back at the end of the line. And I see somebody I recognize. And so I went up to and tapped them on the shoulder and said, are you Woz? And it was Woz, Steve Wozniak, the guy, one of the co-founders of Apple. He's the guy who actually wrote and produced the Apple I, which then became the Apple II. And it's interesting, he actually used to work for me in a funny way, because he never left Apple. He always remained an employee of Apple. I think he's still an employee of Apple. And we paid him, I don't know, a salary of like $1 a year or something. But he never showed up. And, but he had to report to somebody. And I was vice president of advanced technology, and they decided, well, that's who we should always report to, the vice president of advanced technology. So he reported to me, but I've never seen him. And so I asked my boss, who was actually the former vice president of advanced technology, well, how do you do the performance review every year? And he said, oh, that's very simple. You say, you did about the same as you did last year. So anyway, I went up and we said hello and talked for a while, but then they started boarding the plane, and he, of course, was flying first class, and Georgia Tech was flying me economy class, so I never saw him again. But Woz was a great technologist. He really was. He was a hacker. And in the good sense of hacking. I'm actually a member of the Hacker Society, and these are all of these people who are proud of their ability to make something work and tinker around and make it happen and do things that people don't think is even possible. And he built the Apple I and the Apple II and produced color out of the Apple II, and nobody thought you could do color. And he did it by these cute little tricks and so on. And after Apple was successful, he then sort of left, although he stayed as an employee, and he decided he ought to really learn about computers and computer science. So he went back to Berkeley under a fake name and got his undergraduate degree in computer science. And he actually said later that, you know, he thought he really understood all this about computers. He was a whiz at it, and he was amazed how much he learned going back to school. He was a great technologist. He's a great person. I went and had lunch with him one day because I felt I had to beat him. So we had lunch, and he bought me lunch, even though I was on I could pay with my expense account. He paid with this. He took me to a diner. Everybody greeted him as he walked in, and the whole lunch was about $10. And he offered to pay. Yeah. But he was a technologist. The Apple I was impossible to use. The Apple II, if you brushed the wrong button, it crashed the computer. The power switch was easy to hit, and it would turn it off, and you'd lose all your work. And there were all sorts of obscure things you had to do to make it work. And later on, he developed a remote control that would control everything, but you could never figure out how to work it. It had like 89 buttons on it. So he is the ultimate technologist. And that's kind of what I'm here to talk about, is the difference between what the technologist builds and what designers build. And actually, I'm going to argue there's two species out there in the world. There are people and there are machines. And engineers are really good at working with those machines and catering to the needs of the machines, and developing something that the machine needs to function. And the stuff they can't do, they leave to people. And so we are forced to act like machines. The problem is the way that machines work and the way that people work are dramatically different. Machines require high accuracy, high precision, and often repetitive operations. And we are really bad at being accurate and being precise and at repetitive things. Now that we're starting to get automation, the argument is, oh, but a person must always be in charge. And so with the automated cars, there's always a person watching over it in case something goes wrong. Come on. Think about it. You're driving for an hour and everything is working perfectly, and then something goes wrong. You're supposed to fix it right away. This happens in aviation all the time. You fly, it's an 11-hour flight from San Francisco to Japan, and the pilots taxi the airplane manually out to the beginning of the runway, then they push a button, and then 11 hours later it lands at the airport at Narita, and then they have to manually taxi back to the gate. And what happens if something goes wrong in the middle? Where are they? So I actually did this flight once. I flew with Japan Airlines, and they brought me into the cockpit. I sat with the pilots as we went up and down, and they had nothing to do. So you're in an airplane, and you're flying along, and something goes wrong. And there's been a number of incidents like this. In one case, they were losing fuel, and they didn't notice it, so the automatic pilot was compensating, and now the more and more fuel was dropping, which means the plane was really unbalanced. No fuel in the left wing, a lot of fuel in the right wing, and so it's tipping over. The automatic pilot is completely compensating, and then the automatic pilot says, oh, sorry, I can't compensate anymore, it's all yours. And the plane starts diving to Earth. Okay, you know, these airplanes are 5 or 6 miles up, and it starts crashing to Earth. You have a couple minutes. And you have really well-trained pilots who have been trained in almost anything that can possibly go wrong. So they figured it out, and they fixed it. And in this particular case, they did get the plane under control again, and they landed safely. And a lot of passengers were thrown about for a while when it first started diving, but nobody was injured, and fine. Now imagine the automatic car. You're driving along, and then something goes wrong. You probably have about a half second to respond, with drivers who have no training whatsoever and no clue as to what's going on. So there's the interaction between technology and people. And as we start designing these automated systems, we really better understand people better and what's going on. So we have machines and we have technology, and who does the in-between stuff? It has to be people who understand people, but they have to understand technology. You need somebody who knows both. And that's the role of a good designer. And so we'll continue on that, but you really have to know both. Now, part of the problem is that engineers think they understand people. Probably most of you think you understand people. You've been a person all your life. And especially if you're in an engineering school, you're taught logic. And so you love to be logical. And I deal with engineers all the time who build things, and I say, nobody can use that. And they say, yes, they can. And they explain logically why it's a sensible and proper way to do things. And I have to tell them, their problem is they are too logical. So, remember the cover of the book? Which is the salt? If you haven't read the book, you don't know what I'm talking about, and shame on you. So, which is a salt shaker? The one with 3 holes or the one with 1 hole? And the answer is, yeah, how many people think it's the one with 3 holes that's salt? Right. How many people think it's the one with 3 holes is pepper? Right. I've done this question all over the world, and it's about half and half. And everybody is convinced they are right, and they can't believe that somebody might believe the other. I have a friend, Bill Buxton, who's a designer now working at Microsoft, and he gets mad at me all the time, insisting that there's no question about it, which is correct. Well, what you mostly do in restaurants, isn't it, is you pick it up and you shake it on your hand to see which it is. And the logic is clear. If you have salt, you use more salt than pepper, and you want more holes, and so 3 holes is clearly salt. The problem is if I ask the other people, they say, yo, no, 3 holes is clearly pepper because I want more pepper than I use salt. So perfect logic in both cases. Let's try another one. Suppose I was showing slides, and I've shown you and I have a controller in my hand. And there are 2 buttons, one's on the right and one's on the left. Which one gives me the next slide? How many think it's the one on the right? How many think it's the one on the left? Now, what if I were in Israel or Cairo and asked this question? What do you think the answer would be? The opposite. Because there isn't a right answer. It's what you're used to. It's culture. And we write from left to right, and Arabic and Hebrew goes from right to left. Okay, new question. I have a slide projector, and there are 2 buttons. One's on the top and one's on the bottom. Which one gives me the next slide? How many people think it's the top button? How many people think it's the bottom button? So those of you who thought it was the top button, could you imagine anybody would think it's the other? No. Those of you who thought it was the bottom button, can you imagine anybody would think it's the other? No. So where's the logic? Well, let's think about it. Here I am, and here's my slide. Here's one slide, the next slide, the next slide, the next slide. I want the next slide. What's your model of what's happening? If your model is, I move forward to get to the next slide, then it's a top button that I push. If your model is, the slides come to me, it's the bottom button I push. Which is correct? They're both correct. So what should you build? There's no answer to that question. They're both correct. If you're reading your screen on your PC and you've gotten to the bottom of the line and you want to read the line beneath it, what do you do with the mouse? Do you move it up or down? Or with the trackpad, you put 2 fingers or a finger on the pad and you move it up or down? Well, the answer is, what is moving? This was a religious debate, fiercely debated about 15, 20 years ago when the first kinds of screens came out and this started happening. And the question is, what is moving? Is it the text moving down? Well, in that case, if the text is moving, I want to move the text up so I can see more. So I push the up arrow, or I move the mouse up. If the window is moving, I want to lower the window so I can see more. So I push the down arrow, or I move the text down. And that was the standard. For years, we were moving the window. Both are correct. It's just a point of view. But we standardized on moving the window until the touch devices came out. And suddenly, we're touching the screen. And then it made sense. I actually touch and push this text up. And so it was really bizarre. Apple had this problem. They said, well, you're pushing the text up, and now you go to your Apple PC, and you move down. So no, we're going to standardize on you always move up. And some of you were very confused. And even today, I use an Apple computer where the guy refused to do it and said, no, I'm going to keep the proper way, the old way. And Microsoft has not yet switched, because nobody knows what to do. This is, by the way, a real problem in airplanes. So here's the attitude indicator. It's a round display, or nowadays it's rectangular. And you show the horizon, and then you show, actually I'll do it differently. This is the horizon, and this is the airplane. And now the airplane is going to bank left. So this is the airplane. It's going to bank left. Oh, that's a problem. Left. That way. So bank left. So do I make it look like that? Or do I make it look like that? So the question is, what moves, the airplane or the horizon? If I'm inside the airplane looking out, as far as I'm concerned, the horizon has tilted. If I'm flying in another airplane behind that one, watching that airplane, it's the airplane that's tilted. So which should I use? An airplane in design language is called inside out versus outside in. And the answer is the aviation community can't decide. And there are airplanes that use one method and airplanes that use another method. And there are even some airlines that they have 737s, say, using one method, and then they bought some second-hand 737s from another airline that uses another method, and now they have these 2 different methods. And so pilots certified to fly 737 using inside out can't fly the 737 using outside in. And which is correct? They're both correct. Actually, the Human Factors Journal publishes hundreds of articles about which is correct, and arguing and arguing and arguing. But that's the whole point, is engineers love to design by logic, and I say you cannot design for people the way you want them to be. You have to design for the way they are. And that's hard. And that takes a special kind of thing. And that's one of the things I did in this book, was try to argue for at least observe the world. Watch it. Look around you and see the way people do things and the way people really behave, not the way they say they behave, but the way they really behave. And we have to design for the way that people really behave and the way that people really think. And that's not so easy. And the models that people have about the world are often wrong. So that, you go into a room and you're really cold, so you want to turn up the heat. And maybe it's really cold, so you want to turn it up, you want to get hot fast, so you turn the thermostat all the way up. Or you want to warm up your oven, so you turn the thermostat all the way up. And then when it reaches the right temperature, you want to remember to go back and turn it to the existing temperature. And that's a model that says that it heats faster if you put it on full heat, on the high temperature. But it's wrong. Because the way that most of these things, it could be right, by the way. It could absolutely be right, but that's not how these things work. They're what's called bang-bang controllers. They're usually all the way on until they reach the correct value, and then they turn all the way off. But people waste a lot of energy because they do that all the time. So how do you solve that? Well, one way to try to solve it is to try to give them some feedback and try to give them a model. The new Nest thermostat does that. The Nest thermostat tries to say, when you set the new temperature, it says, okay, it's now 65, and you set for 72, and it turns red, so it tells you, I'm now heating, and then it will say, in 15 minutes. And that's really kind of nice. So you know that it has turned on the heater, and you know that it knows the current temperature and the target temperature, and you know that it's going to take roughly 15 minutes. And in fact, if you think maybe turning it up faster, hotter will be faster, you can try that, and it will discover that the 15-minute time doesn't change. Well, actually, it does change. That's unfortunate. I hadn't thought about that. Because if you turned it up to 90, well, it's going to take longer to get to 90 degrees. But it's doing its best to try to give you the right model. And the Nest thermostat, I don't know if all of you have heard about it, but it's this brilliant, beautiful automatic thermostat. What they tried to do was say, look, these are two ex-Apple guys. In fact, it's the guys who did the iPod, who quit and started their own company. And they said, thermostats, programmable thermostats, are almost impossible to program, right? You get this, you're trying to say, what time I should go up in the morning, and then maybe there's an afternoon setting, and then maybe there's an evening setting, and then there's a night setting for Monday, then you have to do it again for Tuesday and Wednesday and so on, and you finally get it all set, and then eventually you want to change it? Yeah, forget it. So this thermostat doesn't have any such settings. You basically just set it for whatever temperature you want. And when you go to bed, you turn it down. And when you wake up in the morning, you turn it up again. And after a few days, it says, I get it. And then in the evening, it just turned itself down. And in the morning, just before you wake up, it turns itself on. And it also knows how long it takes to get up to temperature, so it turns itself on earlier, so it'll get up to temperature when you've asked for it. And if you're not in the house for a while, it notices that nobody's walked by it for a while, so it goes into away mode, where it basically turns itself off and keeps the house within, so it never gets to freezing, but never gets too hot. So in mine is set so it never gets below 60, it never gets above 85. And it just learns for you, and it gives you this feedback. Well, that's what we need more of. And it's really easy to make bad things. And the reason is because we don't think about it. So what does it take to do the thinking? Well, it's what I call human-centered design. It's that we start off by watching people do what they're doing. Try to understand how they do it and where they have issues and problems. We don't ask people. Ask people what they have trouble with, and they'll tell you what's the problem with today's devices. And that's not what we need. We need to know, what are you trying to accomplish? Because maybe there's a whole different way of doing something. It's actually, one of the rules of a great designer is, don't solve the problem you were asked to solve. I love to do this when I teach design to engineering students and MBA students, because you guys are really good at coming up with solutions. So I give you a problem on day one of the class, and on the next week you report, and there's fantastic solutions, drawings, engineering drawings, or sometimes even models, and the MBAs always have spreadsheets showing how much it's going to cost and how much profit we're going to make and all that stuff. They never stop to ask whether it's the right problem. We spend a lot of time solving the wrong problem. So what a good designer always does, and this is what we mean by the word design thinking, is we step back and say, what's going on here? What are the real issues we're trying to address? Designers are interesting. Universities produce specialists, people with deep knowledge. You'll find that in all of the departments that you have here, except maybe architecture and design. that mechanical engineering is divided up into many different specialties. Quite often, this specialty doesn't understand anything about that specialty, even in the same department. And computer science the same, but electrical engineering the same, and civil engineering the same, and all your departments very much the same. And we hire the very best professors in the world in their field, which means they're very narrow. So it means they have great, deep knowledge, but often narrow. When we go out to build things in the real world, we need horizontal knowledge. We need to know a little bit about everything because we have to combine an understanding of human beings and business and social structures and mechanical engineering and manufacturing methods and computing methods and electrical engineering and microprocessors and maybe nanoparticles and all sorts of things and put it all together. And so the great designers are actually generalists in which they know a little bit about everything. The problem is that the university does these specialties, and so most of us learn just a narrow specialty. I mean, I was trained that way. I was trained as a circuit designer. My first degree is in electrical engineering. Actually, my second degree is electrical engineering. And I was really great at designing circuits, and first of all, I couldn't write, and second of all, I hated people. Well, I didn't hate people, it's just that they got in the way, you know? I design these circuits and then people don't use them right. And if they really didn't have people, then my stuff would work really well. And I got into psychology completely by accident because I was a graduate student in electrical engineering at the University of Pennsylvania, and I really wanted to work on computers, and there was no computer science department. And they kept saying, oh, we're going to have one, we're going to have one, but I couldn't wait. And if I stayed in electrical engineering and had to learn about antenna theory and stuff I didn't care about. And so just then the psychology department got a new head. He had a PhD in physics and was doing what was called mathematical psychology. And I decided that I really wanted to build computers, but gee, what they're doing is just what I want to do except the opposite. So the most powerful computer is the human brain, so I could go over there and study it and still do exactly what I was doing. And I did. I switched over, and I used all the mathematics and all the circuit theory knowledge I had and all the stuff I had to actually, I helped invent a new field, which was called human information processing, hence the textbook. By the way, when the textbook was published, it was not used in many schools because actually the students loved it, and the professors were scared to death of it because it was all about this scientific stuff, and you could derive. Psychology used to be memorizing what people did, and we made it into, you understand fundamental principles, you derive the rest. Anyway, so I switched over and sort of did the same thing for many years and studied people's memory and decision-making and so on. And then moved, my first job was at Harvard, and then I moved to the University of California, San Diego as one of the first faculty members there. I got there before anybody had ever graduated. And, but after there for a while, the 3 Mile Island nuclear power accident happened. And so they called in a bunch of psychologists to try to understand why people were so stupid and made such stupid errors. And I had been studying how people do things, and I had written a couple papers on human error at that point, and so they called me in, and the team that I was part of looked it over and said, you know, if you designed a plant to cause errors, you could not have done a better job. 4,000 controls and knobs and indicators designed by engineers, so you measure what you can measure. You don't measure what people need to know. You measure what is possible to measure, and you take your straight edge and you make straight lines and you put, okay, here's a bank of 45 switches, and here's a bank of 45 meters, and here's a bank of another 13 switches, and they all look the same. And they're not even, and sometimes they make errors. So this is switch 1, 2, 3, 4, 8, 7, what? And so in this case, the operators actually did, I think, the proper thing. And they did a misdiagnosis, but it was a very sensible misdiagnosis, and the early feedback they got was consistent with the misdiagnosis. That's the problem with mistakes. There are two kinds of errors, mistakes and slips, I was arguing, and mistakes are when you misdiagnose the situation, but you're intelligent in misdiagnosis. This happens in medicine a lot. When you misdiagnose something, it fits all the symptoms, or a lot of the symptoms. And when we give the first cures, it often helps you. So it takes a long time to discover it's wrong. That's the worst kind of error, misdiagnosis. A slip is when you accidentally, I meant to hit switch 7 and I hit switch 6 instead. That's much easier to detect because I didn't do what I intended to do. So anyway, I realized suddenly for the first time that, oh, my background in psychology and my background in technology is what's needed. Because for design, you need to know both. You need to bring them together. And that sort of started me on this career. And I wrote this book, Design of Everyday Things, Psychology of Everyday Things, and I didn't know about designers. I didn't know there was a real profession called design. And so I've just rewritten the book 25 years later because the principles that I gave there are still the same. The technology is completely different. And I realized the importance of emotion. So most of you engineers hate emotion, right? It's one of those old-fashioned things that it gets in the way of logic and doing things sensibly. But on the other hand, you really love some of your devices, don't you? And you love some cars, and you just, oh, I really have always wanted a Porsche or whatever. Why? What is it that makes it so good? And why do we like the gesture films, even though it's much harder to type on a gesture film than on a BlackBerry? The BlackBerry is old and clunky and old-fashioned, and the gesture phone is just fun. And I love to ask people to do things on their gesture phones, which is Android or iPhone, like change the time zone. And they say, sure. And they go in and they say, oh, it's in the, yeah, there. And let me see, it's under, no, not there. Oh, no, here. Oh, no, that's not right. And they back up and then they forget to take off the automatically adjust to the local time zone, and then you can't change it if that button is checked. So you have to go back and uncheck it. And then when they're all finished, they said, see, isn't that easy? 2 reasons. First of all, it's fun. And second of all, they blame themselves. Oh, yeah, I forgot. It wasn't in there. It's over there. It's my fault. And that's where emotion comes in. And when it's pleasurable to do, and it's changing the time zones is not something you do very often. So it doesn't matter that it takes a bit of time. But enjoying it is wonderful. So that's why we love some cars. Some of us love manual shifting because with a precision car, it just feels good when you switch gears and so on. And you feel like you're in control. And some of us like special cooking knives because we just love the precision of a really sharp knife that's well balanced and the way it chops and the way you can cut. And some of us like other things, but everybody has things they love and things they don't like. And they often have nothing to do with the logic. And quite often we love these things even though they don't work as well as this other thing. But the other thing is ugly and clumsy to use. Emotions are really important. And I've added that to the book because there's enough scientific knowledge of emotion to be able to put it in and understand there are different levels of emotion that have different things. But here's an example. It's from my TED Talk. Some of you may have seen it, but it's a really powerful example. Is that I put on the ground a big plank that's this wide, and I walk on it. No problem. And I can jump, and I can bend down. I can jump. No problem. I'm now going to take this plank and put it 50 meters up, so it's 150 feet off the ground. I am not going to walk on it. Now, and my whole body tenses up, right? My stomach muscles go, what? And my heartbeat changes, and I sweat. And why? I've showed you that I can walk without even looking. I don't have to look at the plank. And I can jump up and down, and I can do all sorts of things. Why is it that moving it up changed it? Because it's the automatic, what I call the visceral nervous system, which is scared to death of heights for good reasons. Now, people can overcome that, just like we don't like bitter tastes, and yet some of our favorite foods are bitter. But it takes work to overcome fear of heights. And actually, if you like coffee, if you like beer, the first time you had coffee or beer, you disliked it. You had to develop, you had to overcome the innate taste, because the way the taste system is developed, sweet tastes are nutritional and bitter tastes are poisons. There's a really good correlation there. So it's really important to take that under control. And how do you do that? Well, what designers do is spend a lot of time trying to observe people the way they work and what they like and dislike and what the real issue is that we should be designing for. And then the same way with the solution. We view the solution by trying them out. We prototype them. We say, you want to study a train? Okay, I'll take these seats and make believe they're the train seats, and we'll have people sit in them and try to do things and eat lunch and do their work and eat lunch with their laptop open and also with the garbage bag or maybe whatever, and figure out how to do it. And we prototype, and we then go back and rethink their observations, because we never get it right, never. Because actually, if you do the perfect thing that really helps people, guess what? They'll say, oh, this is wonderful. I can do something else with it. Look, I can use this for all sorts of other things, which now means that they're doing it for things I never thought about, which means I have to change the way I designed it. That's a neat thing about design, actually. If you're successful, people do wonderful things. So you need to be a great observer. That's the first step. Watch people and take people the way they are, not the way you want them to be. I have two more topics I want to cover, which is we're in a very exciting period of technology. Things are changing very rapidly. We've moved the phones to gesture phones, which is done really badly, by the way. We forgot a lot of the principles. So with gesture phones, it's really very neat, but do you tap it once or twice or 3 times, or left or right or up or down? The old menu system we could explore and see what the possibilities are. Today, it's kind of awkward. And people often don't know. I was just showing somebody that when you're watching a video and you want to stop it, well, in the bottom left-hand corner, there's a little triangle which changes to vertical bars to start and stop it. And it's really hard to get to. Just touch any place on the screen and it stops. And touch any place on the screen again and it starts. How would you know that? There's no way to discover it except by hitting it by accident or by me telling you. And there's a whole bunch of things in these modern systems like that. Reading your mail and you want to see if there's any more mail, drag the mail down from the top until it springs and let go, and then it says checking mail. How would you know that? Well, you know it because I told you. And there's a lot of other things that are just bizarre. So we'll get better. But that's not what's exciting. What's exciting is things like 3D printing. Additive manufacturing, where for the first time we can make structures that are unlike anything we've ever done before, that are lighter and stronger, with internal structures and internal holes that you couldn't make by any other method, that we can mix. So material science is dramatically changing, because in additive manufacturing, we don't melt metal and then anneal it, but we use often powdered, and then we try to melt it or try to glue it, and it's very different properties. But we can do something we couldn't do before. We can mix metals and plastics and combine. And we can even change the mixture as we go at different levels in the device. So actually, 3D printing is in its infancy, and it's really slow and tedious, but General Electric is making real airplane turbine blades, the ones that go into the airplane. They're not prototypes, they're the real ones using them. And we can print food. We can grow food. Instead of killing animals and cutting off the steak, we can start to grow the cells. And we can print medical devices and print medical prostheses. In fact, large numbers of joints, artificial joints, and hearing aids and other things are now being printed to spec. And there's all sorts of new things that are coming along, all sorts of new sensors, all sorts of displays. And they raise all sorts of wonderful examples of things that we can do and things that can help us. The wearable Google Glass, which so I can say, oh yeah, your name is Kotz. Yeah, we really met. Did we really meet then? Etc. Thad Starner does that to me all the time. He says, remember the last time we talked 6 years ago, Don? Well, you said this and I said that. Well, I've been thinking about it ever since, and here's the answer. And I say, huh? And but it also brings up a lot of societal issues about privacy, about is it ethical? One of the things that happened when I wrote this book 25 years later was that technology has changed a lot, but people have not changed. But people may change. We're starting to do implants. I have better vision than I've ever had in all my life, so I take off my glasses, I can actually read things and see you, because I don't have lenses anymore. But my lenses have been taken out and replaced by plastic. And that plastic can't be changed. It's fixed, which is why I have to wear glasses still to be able to see close up. But that will change. We're going to have deformable lenses that will focus just like the real lens, and back better. That will get rid of astigmatism, and that will probably have some telescopic vision, because what it can do is focus on greater focal length than the biological lens. And what about baseball players, pitchers, they injure their arm and they have an operation and they change the bone structure, and guess what? When they recover, they're better than they were before. So some pitchers who have no trouble want to have that same operation. And of course, there's genetic modifications. And implants, we already have implants, cochlear implants, so the deaf can hear. But maybe we could have a cochlear implant that would enhance the listening, the hearing of normal people, otherwise normal. There are going to be a lot of ethical issues and a lot of advances. And of course, I could go on and on about this. You know what they are. But there's all sorts of other issues like environmental concerns and reusability and product lifetimes. And one of the problems is we tend to view things in isolation. The electric automobile has no emissions. Wow, we should all switch to electric automobiles. But actually, it turns out they're not necessarily any cleaner than gas-powered automobiles. Because how do you make the electricity? The source of the electricity matters a lot. If it's coal-fired electric plants, that's not any better. And maybe if it's wind-powered, that's okay. But wind-powered, the turbines, how do you manufacture the turbines? Where are they made? And what are the byproducts of that? And how do you get the electricity from the turbines to where you need the charger? And how do you dispose of the batteries? And what kind of chemical residues are made in the manufacture of the batteries? It's pretty poisonous stuff. And so when you look at the whole system, it turns out that not all electric cars are actually superior to what we do today. And a lot of it has to do with the battery manufacturing technique and the way we generate electricity. And we have to learn to take a much larger view. I mean, there's a really good example that one of the orange juice manufacturing companies that makes orange juice in Florida and packs it in containers and sends it all around the United States was very concerned about environmental impact. And so they thought, gee, we have to ship all this heavy orange juice all around the United States in trucks, and that must be the main problem. But they were intelligent enough to hire a good team of people who went off and examined the entire infrastructure, the entire problem. And they discovered that was not the problem. That the most damaging part of to the environment was the fertilizer they used on the orange trees. So we have to learn to take a much larger view than we've been doing. We tend to just look at a simple thing. I'm going to make this out of recyclable wood, and see, now I've done good to the planet. Maybe not. The other exciting thing that's happening is just-in-time learning. So there's a big revolution coming on in learning called MOOCs, massive online open courses. That's not necessarily the answer. So actually, we had a session about that today. And I'm doing a MOOC on my course. But what I think is exciting about MOOCs is not what they're doing, but the very fact, for the first time in a really long time, maybe forever, universities are rethinking the way teaching is done. And I predict that the MOOCs will lead eventually to a big change. And it may not be through MOOCs. It may be the MOOCs for the stimulus getting us rethinking. And that 10 years from now, we won't have those kind of MOOCs, or maybe they'll be used in different ways. But it's really interesting. And here's a couple of things. How do we learn today? Well, people teach. We give lectures. It's well known from all the studies that have been done that lectures is the worst way to learn. That's not how you learn. It's the easiest way to teach. Just like I'm giving this lecture now to a lot of people. See, I can give this once a week or 3 times a week and so on. Get it over with. Not how you learn, though. It's good for motivation. And I like to think it's good for what I'm doing now, hitting a general topic with an overview. But if you want to know the details, you have to struggle through it. We have problems, though. First of all, professors are very narrow. And for a lot of courses, we need to know how it applies, and that requires more breadth. Second of all, professors like to think logically. How can you understand this complex topic unless you understand first the fundamentals, and then we move you through. And then at the end of the course, we'll give you some really interesting examples. And guess what? You always run out of time before the end of the course, so we don't get to them. And first of all, what's the dullest stuff you can ever learn? It's the fundamentals. You have no idea why you're learning this stuff. And so one of the things that problem-based learning tries to do is let's reverse it. We'll start off by saying, which is the salt? We'll start off by giving you an interesting problem and ask you to solve it on day 1, and you don't know enough to solve it. And so you struggle, you start to do things, and you come back to the professor for help, and the professor says, oh, yeah, by the way, you want to read chapter 2 of this book. And the same chapter you would have hated to read before, because all this abstract fundamental suddenly makes sense. In academics, we talk in abstractions, because abstractions and generalizations, that's the power of modern science and engineering and technology. But it's horrible to learn. We learn from specific examples. So what we really should be doing is giving people this example and that example and that example. After we've done a couple examples, then you're ready to come back and get this generalization. So I'm not saying not to do deep science, and I'm not saying not to do abstraction, but we have to motivate people. It's all about motivation. There's another interesting example. You know how people make decisions in large companies? So I've been in lots of executive rooms, and both as a member of the executive team, but also as a consultant to executives. And here's the way it works. There's a big boardroom and a big, fancy, expensive table, and people, all the senior execs sit around it. And then often there are chairs around the outside along the walls, and that's where the assistants sit. And they scurry back and forth with papers and so on, and they hand them to the execs and so on. And then they're trying to make a big decision about whether to go forth with this product. And the marketing people come in and they present these wonderful slides and spreadsheets and numbers about sales and margins and profit lines and the competition and so on. And then they go and they either leave the room or they go sit on the edge. And the executives sit there and say, mm. And then one of them will say, you know, the other day my daughter came home, and you know what she said? And they'll tell a couple of stories. And after those stories, they'll say, yeah, we're going to do this. Or, depending upon the story, they might say, you know, that is not going to do it. BMW brought out this wonderful, I really love it, it's on my BMW, it's a heads-up display. So as I'm driving, and I look out about 4 or 5 feet in front of the car, there appears to be a display, and it tells me the speed limit and how fast I'm going and navigational information. And it's really very nice. I would never live without it. It turns out the BMW executives thought it was the stupidest thing in the world, and they didn't understand why anybody would want it. And so the guy in charge of this project finally managed to get it into a test car and get a BMW executive to take it home. And he let his wife drive it. And after a week, his wife said, don't give this car back. I love it. And that's how they make these decisions. And I think here's the issue. You don't make decisions based on the story. You don't. The quantitative analysis, the numbers, were absolutely essential. But we don't trust the numbers, because when you're trying to devise these numbers, they're sort of made up. And they have to be sensible, but we have to make them up, because we don't really know the real answers. And the stories give you concrete examples of what it might mean. And so it's the emotional side and the human side which makes those quantitative analyses real. We can feel it. Or if we have a story that seems to contradict what we just heard, it makes us doubt the numbers we just heard. And so people are people, and in learning it's the same way. We learn from stories. You may notice that I'm telling you lots of stories. because stories are more interesting. They give you particular examples. But again, the good professor will take those stories and then back off and generalize and give you a principle that you've learned from it. And because we learn from concrete examples and from stories, not from abstractions, we have to change the way learning takes place. The other thing is professors refuse to make errors, right? Before you do homework problems in class, you study them at night so that when someone asks you in class, you'll get it right. And I claim, no, you should not know what the problems are. And the student says, how do I do problem 37? You say, what is it? And you read it and you say, oh, that's easy. You just do this and then oh no, that's not right. Well, let me try this and go back and forth. And the students learn that making a mistake is no big deal. Experts make mistakes, but they don't think it's anything special. Yeah, not a mistake. I just went down the wrong path. I'll go back and do this. And, oh, that's wrong. Oh, I made an arithmetic error here. Thank you for pointing it out. And you go through it. Because today, when you do something perfect, and then the student goes back to their home and they can't do it, they say, oh, I'm no good at mathematics. I want to drop out. Or I'm no good at whatever. So we have to actually put in the right role model, which is don't be afraid to make errors or to say you don't know. And the other thing about education that I find exciting, the new approaches, is we now take people and send you through college, and our goal is to feed you with everything you ever need to know for the rest of your life, which is really stupid because a lot of studies have been showing that when you graduate, you don't remember almost anything you've been told. MIT, mechanical engineering department, did this. They asked all their professors in the ME department what every undergraduate ought to know when they graduate, and they got their graduating seniors to take a test on the stuff that every graduating senior ought to know, and then they couldn't do it. What you really need to know is you need to know some fundamental principles, and you need to know how to learn. And that's where I think the MOOCs and the Khan Academy and others are wonderful, because when I'm 20 years out of school and suddenly there's this new thing that happened and I need to learn about it, I can go and learn it by myself. And all this worry about, oh, how do you grade somebody and how do you do it? It doesn't matter. I'm doing it from my own knowledge. I think that's what's going to happen. And a lot of you can take advantage of it, because a lot of you will be the people doing that MOOC, and it's actually going to be, you'll get a lot of income from that way. It's like writing a book. The income comes in, but it's more than the university. It's lifelong knowledge, and it's just-in-time knowledge, JITL. It's that when I need it, I look it up and read it, and I'll work hard to learn it because I need it. And that's what I find exciting about some of the new developments, that it will give you the knowledge you need. Now, one more thing. Designers often know nothing. So let's not talk about Georgia Tech, because I actually like the curriculum in the Georgia Tech Design School. But in a traditional design school, which is usually separate, it's not a university, it's an art school or architecture school, like RISD, Rhode Island School of Design, it's a craft. You spend 4 years learning how to draw, learning about some materials, a little bit about manufacturing technique and building models and prototypes and stuff. And then if you get a master's degree, it's simply more of the same, except you're probably doing more computer-aided stuff. You don't learn any topic matter, and then you've learned all these wonderful skills of making beautiful projects, and you're suddenly asked to do a medical device, or you're asked to design the Atlanta transportation system, or you're asked to design the organizational chart of a company or a health delivery system. And what do you know about this? And designers know nothing. And I used to be really upset about that. I used to complain. I gave lots of talks and so on. But then I started looking more closely at the results that these designers have produced, and I was amazed that some of them were fantastic. And who would have thought of that? That's brilliant. And so I tried to look in more detail, and I actually visited a lot of design schools. I spent a lot of time in schools in Delft and Eindhoven and London, across the United States, in KAIST in Korea, in Shanghai, Hong Kong. What great designers are, in addition to being human-centered and understanding people and having empathy and knowing how to put it together with technology, is quick learners. I have to learn this new topic really fast enough to be able to create something. And how do I learn it really fast? Well, I go and I talk to all the experts and I try to piece it together and I ask questions and I ask stupid questions. What's the most important kind of question you can ever ask? It's a stupid question. Because what is a stupid question? It's one where everybody says, that's obvious. Why would anybody ask that? You must be stupid, right? When you say, why is it obvious? Oh, well, well, we've always done it that way. Well, why have you always done it that way? And sometimes it is really a stupid question or not a relevant question, but sometimes you realize I don't have to do it that way. And if we redid it in a different thing, my goodness, look at what we could accomplish. So that's what I want to say today, is let's understand people, because we're engineers and technologists. Why are we doing this stuff? We're doing it for people. So we need to understand the technology, yes, but we need to understand people. And we need to not be afraid to make mistakes. In fact, the best designs are we make mistakes. Great designers make huge mistakes. In fact, scientists make mistakes all the time, except they don't call them mistakes, right? I'm in my lab, and no, it didn't work out. Or, oh, I learned I shouldn't do it that way. I should do it this way. We don't call them mistakes. We call them learning opportunities. And don't be afraid to ask stupid questions. Thank you.
We'll do some stupid questions. Does anybody have any?
You might remind them they have to go to the aisle.
So I'm a grad student. Is it on? Hello? Okay. So I'm a grad student in the industrial design program, and I really liked what you said about redefining the problem. But in my experience, kind of in the studio environment, we are kind of given 3 or 4 weeks on a project, and the teachers kind of say to us, okay, now you have about 2 or 3 days to think about this problem, and then you're going to move on to the next step in the process. So what would your kind of advice be in that scenario where we're like kind of narrowed into this very specific problem, and then we're not really supposed to think about it that much anymore once we decide on that?
Well, it really depends what the professor, what you're actually is trying to be taught there. It's possible that what you're learning is a very particular technique, and maybe the problem isn't so important. But so I can't really answer that question, because I would need to know why you were asked to do that and why you were given this limited time. And one of the problems we face in the universities, well, you know, we have quarters or some. Are we in the semester system here? Yeah. We have 15-week semesters. And so that's limited time to learn a lot of stuff, and it's hard to do a real problem. And this is especially true in computer science. All people in computer science, first of all, learn to start a program from scratch, which is never true in the real world. And second, they're always toy problems, because often you work on it alone, and you have to finish it in this semester. And you often don't start until maybe the middle. And a real problem, a real programming problem, can take 200-300 people 2 years to do. And in industrial design, it's similar, that the design researchers, they want a couple months often to figure out the research, or certainly a month, or even a couple weeks. But what they do is, in the first couple, suppose I give a month, what will happen is in the first week, they're still trying to understand the problem. And in the second week, they figured out the problem. In the third week, they're still trying to figure out the various solutions. And the managers are driven crazy. And because there's only 1 week left. And the magic occurs in the end. And sometimes actually giving you a limited amount of time makes you more creative. But again, for your particular instance, I would have to talk to the professor and say, well, why did they have so little time? The professor said, we understand the need to be creative and understand the real problem, but that wasn't the purpose of this course. Maybe that's what they would say.
Maybe we should arrange that meeting.
We're supposed to use this? Or
Yes.
Speak loud?
Yeah.
Hello. So my question is really about the language of design, because my experience in practice in designing products and graphic design and motion graphics is that design is a nonverbal language and it has its own set of rules, and that it only has a bare correlation with sort of the verbal language we have to use to design, and that in fact even when I teach it that way. So how do we
Yeah,
how do
so
we make
why do you
that
think that's
correlation?
different than mathematics, or you think it's different than any technical vocabulary, or the words that we use? I mean, come on, take a look at what the physicist says work is. If I take this really heavy 100-pound book and I hold it like this, I'm exhausted, but the physicist says I'm doing no work. So every field has its own technical vocabulary, and design is no different. And actually, the way to get around that, that's why I like to use affordances and signifiers, because the average public hasn't heard about those, doesn't understand, so it sounds like I must really know what I'm talking about, and it's deep and so on. But, and the fact that it's a visual language, yeah, it is. And visual languages are very powerful, and actually, probably most engineers kind of do sketching too. When you write notes, why do we use paper and pencil instead of computers? In part because I can put a note here and then a note there and an arrow connecting them, and then I can show these relationships and I can move them around. That's visual thinking partially. And visual thinking is very powerful because we use space to help organize our thoughts. And as we learn to be good artists in part because when you're doing physical products, you have to worry about the constraints so it fits. So we start off by trying to draw a picture and see whether it makes sense. Eventually, we may have to build it or at least have a computer model of it to make it work. So visual thinking is very powerful for lots of disciplines. It's the way that musicians think too, visual and time. And we often map time into space, right? And so I would say it's a very powerful technique that more people ought to learn. As for the language, yeah, that's a problem all technical disciplines face.
I guess I think sometimes people have a hard time actually thinking in that language. And I think mathematics is a logical language, and I don't think that visual design is a logical language.
No, no, visual, actually it is. There's actually there's a lot of interesting psychology is being done understanding visual thinking and the role of diagrams. And it's interesting, mathematicians love to say we do it by proof. We don't use these pictures, and people who draw pictures are weak. If you actually study real mathematicians, they have these images in their head, and they often do draw pictures, and they do geometric things, but they will disguise it. And the proofs are incredibly messy and all over the place, but when they publish it, it's very nice and logical and makes sense, right? It's the same way we write up experiments. We had this hypothesis, we did these tests, we got these results, and here's the conclusion. That's not how we did it at all. We futzed around in the lab, and this worked and that didn't work, and then we write it up as if we meant it all along. So.
Hi. I don't have a stupid question, but I'd like to hear your opinion about the salt and pepper question. So, well, I say that the one with 3 holes is salt, because if you add another dimension, which is cost, salt is cheaper. Therefore, the one with 3 holes should be salt.
You're entitled to your opinion. It's just that I'm always going to shake it on my hand and see what it really is. But I would recommend for people designing salt and pepper shakers is make them transparent.
Okay, we'll do that.
Hi, my name is Leon. I'm a sophomore chemical engineer. You were talking about learning and how the learning system right now isn't the best, but it's kind of, as like a chemical engineer, a prerequisite into getting jobs, or at least going into companies that are already made. How would you suggest that I approach learning, I guess? Because I do feel like I would like to have like just-in-time learning, But is that mature enough for me to, I guess, go out and do my own thing? Or do I still need the foundation of this knowledge?
Well, yes.
Yes.
So, I mean, the argument about how we should change the learning practices is actually aimed at the professors because they're the ones who have to implement it. And so you have to deal with what we have. But you can also be doing your own learning, and in fact, you're a much more exciting employee if, because when I come to hire people and I look at all the recent graduates, they all kind of look the same. And actually, I'm not necessarily happy with GPAs as a way of discriminating. When I was taking graduate students at UC San Diego, if someone had a perfect GPA, I didn't want them. Because it meant they didn't take any risks. It meant they didn't go off and take this course because they really wanted to learn it, even though it was really too hard for them. And I actually took one student who turned out to be brilliant in the end, who had flunked out of Berkeley. We had to work really hard to get him into graduate school, by the way. And, but he flunked out of Berkeley because he was too smart. And he just got bored by what was going on and did his own stuff. And he was brilliant. And so, but what you need to do is, yeah, if you're interested in something, go learn more about it. And then when you apply for the job, they'll see that, oh yeah, you took all the standard courses and yeah, you did okay. But you tell them maybe I did this really exciting thing in chemical engineering. That's what will excite them. That's how you distinguish yourself from everybody else who took all the same courses. And get away from comparing GPAs.
Thank you.
You know, the GPA only matters for two things. If you're going to graduate school, they look at it. And in your first job, they don't have any other way of discriminating, so they look at it. But after that, nobody gives a damn.
Idan, how are you doing? Okay, so if you were given the opportunity to ensure that a fundamental concept in regards to human interaction and design of your choice was taught and comprehended to all engineers and scientists, undergraduates, and they walked away from college knowing that concept, what would that fundamental concept be of your choice?
Well, I'm trying to figure out a good way of stating it, but it has to do with the fact that people evolved to interact in the world, and we have very complex systems. The emotional system and the cognitive system work in parallel. They're both equally important. Cognition is about trying to understand the world. Emotion is about making value judgments, and they both go together. And so we really have to, as we design whatever the technologies, we have to understand the people that are going to be using it. And that's enough. You don't have to know how to do it, but you may want to call in the experts who can help you. Just like you don't have to know all the technologies that are relevant to something you're doing, and you call in the other experts. But the need is that there are people who really can understand the people and translate it and work with you. Because I think lots of engineers don't even realize that there are professions that are specialized and that what they're doing isn't necessarily appropriate. So at least I want them to have the sensitivity.
Thank you.
And that's actually what the design of everyday things is about. The book, the first book, I don't know whether the revision will be just as good because it ended up a little bit thicker, but I promised I would keep it the same size. And every time I added some new material, I would delete the equivalent amount, but I failed. But the whole point of it, it was assigned as a quick reading. You could read it in a week or two, and it sensitized you to these issues. You weren't a designer at the end, but you started to understand what it might be, and that's what I thought was most important.
Hi, my name is Juan, and I must admit that I eat while I drive. And actually today in the news I read about something that Kentucky Fried Chicken came out with, which is like a meal that can fit in a cup holder. And at first I thought this is genius, and apparently the article about it talked about all the research that KFC did to look at cup holders and the sizes and the cup holder meal that they figured out fits in 83% of cup holders in all cars. So they did all this research. So I was just kind of wanted to get your reaction on that, of what you think this kind of design is. Is this really human-centered? I mean, at first I thought, like I said, I thought it was genius because I'd always been thinking, we have drive-throughs, we get the food, why can't we eat while we drive? But I don't know, it's a little dangerous.
So actually, here's a conflict that happens. It won't happen often. That what it's probably, if you did some research on people, and it turns out that lots of people are rushing out in the morning, and they need food, and they stop off, and they get a drink, or they get, and so another set of people studied this and decided that people needed something they could eat while driving, and so they made this nutritional drink, and so you could sip it with a straw while driving, and it's sort of the same thing. And I think Kentucky Fried Chicken or KFC was right. This is a real need, and people like it, and they'll buy it. Now, there's a societal issue. Does that make driving more dangerous? And I suspect it does, but the real danger in driving is distraction from while doing other tasks, and especially the distraction that takes your eyes off the road. And that's why setting your navigation system or reading your email, or even simple, people try to tweet while driving or instant message while driving, is really dangerous. And if you drop something on the floor, you should not bend over and pick it up. But Virginia Tech, I guess, has done all these studies with instrumented automobiles. They put video cameras all inside the automobile, and they give it to people for a year. And they show people turning around and scolding their kids and dropping something and leaning over and picking it up. And if your eyes are off the road for more than 2 minutes, it increases the chance of an accident. And they actually have lots of accidents on their records. Now, it's possible that you can eat without taking your hands off the road. And although you're only using one hand to drive and one hand to eat, I'm not sure that's so dangerous. If you look at cell phone usage, banning the use of cell phones while driving, well, it's not a bad idea to ban it, but actually that's not the danger. The danger is not handheld cell phones. The danger comes in the dialing, and the danger also comes because I'm distracted, I'm mentally distracted. I'm holding this conversation with somebody while I'm trying to drive, and so although I'm looking straight ahead, I don't see the stuff in front of me. And I suspect that would not be the problem while eating. So it may turn out to be okay.
So,
what are your 3 favorite buildings in the United States?
No, actually, I refuse to answer the what are my 3 favorite or my 3 hated most, because I just don't want to answer those things.
Which 3 buildings do you admire?
Nice try.